Hello, and welcome to the third part of our survival guide to mathematics. In this part of lesson 2, we're going to look at two ways to solve simple first-order differential equations of the type that you'll encounter during this course. The first method is direct integration. This requires an ordinary differential equation that we can easily rearrange to make the parameter we wish to find explicit. Once we do this rearrangement, all that is required is a straightforward integration. The second method is one technique that can be used when the ordinary differential equation can't be rearranged. We're going to revise the use of integrating factors, where we make use of the chain rule to collapse two summed terms that contain our parameter of interest into just one term. The integrating factor example I've chosen also involves integration by parts, so this is a good opportunity to remember how to do that too. So, let's start by thinking about a simple differential equation that we can easily integrate. So here on the board, I have put one such differential equation. Now, when we do the analysis of viscoelastic liquids in lessons to come, we will see differential equations of this form, and so I've written it with the parameters that we'll see when we encounter it the next time around. So here tau is stress, t is time, lambda is something called a relaxation time. So what we have is the derivative of stress with respect to time, d tau by dt, plus some function of stress, plus tau over lambda, is equal to 0. Now that equals to 0 bit is really useful, because of course we can simply take the term of interest which includes tau, that's the tau over lambda term, over to the right hand side of the equation, as I've done there, and then we can simply write our integral and directly integrate. It's a dream scenario. It's an easy way to solve a differential equation. And so when we integrate, we simply get that the natural log of stress, the natural log of tau, is equal to minus t over lambda plus whatever constant of integration results from that integral. So we need to eliminate or find that constant of integration, one or the other, depending on what the initial conditions are. And let's just say that we've got a cunningly chosen initial condition that, at 0 time, our stress, tau, is equal to 1. We know that the natural log of 1 is 0, time is 0, therefore our integration constant is 0. And so, if we want to find stress now as a function of time, we can simply take logs of both sides and find that stress is going to be the exponential of minus t over lambda. So, direct integration in this case has been a really straightforward way to solve this differential equation. However, life isn't quite always that simple. Let's suppose that a very similar analysis has resulted in a very similar differential equation, but now the right-hand side is no longer 0. It's a function of time. And again, we will see differential equations of this nature later on in the course. So, what do? We can't easily rearrange this now into a form where we've got all the taus on one side and all the t's on another. So, there is a nice approach we can take, called the integrating factor approach, that tries to make use of a product rule expansion on the left-hand side to try and gather together the terms that we need such that we can use direct integration. So let me explain or remind you how this works. So, if, for example, we can rewrite our ordinary differential equation as I've just put on the board, where each term is pre-multiplied by a certain term that I've labelled I here, and we can see that if every term is multiplied by that, it's the same differential equation that we started with, since we can simply eliminate I all throughout and result in where we started. Now, the cunning part is our choice of I. And what I'm going to say is that if we focus on the pink term on the left-hand side, that tau over lambda term, I in this case should be the exponential of the integral of whatever pre-multiplies tau, in this case 1 over lambda, and we integrate with respect to time. So I'm writing as the exponential of the integral of 1 over lambda dt. And we'll see if we use that definition of I, something rather convenient happens, which is why we've defined I quite precisely in the way that we have. So there on the board, I've substituted in I, and what I want you to do is to focus on that left-hand side. So the first term is the exponential of t over lambda d tau by dt. The second term is the exponential of t over lambda, again it's that same term I, tau over lambda. Now, look at that curly brace and what I've written beneath it. Beneath that curly brace is a contraction of two terms. Let's multiply that out using the product rule and see what we end up with. So that contracted term is a differential d by dt of a product of tau times e to the t over lambda. So using the product rule, if we expand that out, the first expansion would be d tau by dt e to the t over lambda, which is what we find our first term on the left-hand side to be. And then our second term would be simply tau over lambda e to the t over lambda. So I've just differentiated e to the t over lambda with respect to time. And that's what we see on the second term. So a very careful choice of our factor I, our integrating factor, allows us to collapse those two terms on the left-hand side, which were the terms that were giving us problems, into one term, which is really very, very handy, as we shall now see. Because if I can write that sum of terms on the left-hand side as one contracted term, I can simply equate that to the right-hand side and directly integrate. I can directly integrate despite the fact I have time appearing on the left-hand side, because time and stress both appear inside the d term that I'm integrating with respect to. So when I integrate that, d of tau e to the t over lambda, I'm just going to get a term which is tau e to the t over lambda. On the right-hand side now, I have my integrating factor I in orange there, my e to the t over lambda, multiplied by scalar b times time, script b times t. So on the right-hand side now, I need to be careful, because I've got two terms that contain the parameter that I'm integrating with respect to. So I have to use the product rule. And let me remind you about the product rule. So my aim here is to find one term that I can differentiate easily, one term that I can integrate easily, where my choice of terms is the two terms inside that integral. So the one I want to differentiate easily ideally loses the time. So I'm starting off with b times t. If I choose to differentiate that, I'll just simply end up with b, which means I eliminate time from that. So when I rewrite the second step of the integration, it suddenly becomes a lot easier to handle. Let me demonstrate. So I'm going to set u equal to b times t. So therefore the derivative of u with respect to time is simply b. And I'm going to choose the term I'm going to integrate as the integrating factor. And if I choose that dv by dt equals e to the t over lambda, if I integrate up to find v, it's just simply lambda e to the t over lambda. Now, let's write that rule out. So I know my right-hand side now is u times v, so bt lambda e to the t over lambda, minus the integral of v du dt, so b lambda e to the t over lambda. And we can now see that the one remaining integral is straightforward to do. And so if I take that step, I just simply end up with the integral there at the base of the blackboard. Now, consider for a minute if we'd made a different choice for u and dv by dt when we were doing integration by parts. So if we'd done that, if we'd made, I don't know, dv by dt equal to bt, we'd have integrated that and we'd end up with a term involving t squared. So we wouldn't have eliminated t, we'd have made its order increase. And if I'd chosen instead to differentiate e to the t over lambda, we'd have still had a term with e to the t over lambda. So we would have been worse off. So we need to choose our terms when integrating by parts quite carefully, such that we can eventually, preferably within one integration, maybe within two integrations, eliminate the term that's giving us problems. So we there have what the right-hand side equals to, and the integral of the left-hand side is just simply tau e to the t over lambda. So let's write that out. There is my completed integral, complete with my integration constant c that I now need to find. Now, we're going to invoke an initial condition with which to find c. So, again, a slightly cunning choice of initial condition that at 0 time, tau is equal to b lambda 1 minus lambda. If we just so happened to have that initial condition, then rather conveniently, c will equal 0. In which case, I can simply write out the left-hand side equal to the right-hand side without c. And hey, look, that integrating factor that I originally inserted, that e to the t over lambda, now cancels out. And so I simply end up with the result that my stress tau is equal to b lambda multiplied by t minus lambda. And so I have successfully integrated that differential equation by making use of the integrating factor approach. So let's sum up a few key points. The first thing that we saw is sometimes we're lucky. Sometimes we can just get a differential equation and directly integrate it without any extra effort, which is wonderful. However, sometimes we can't do that. In fact, a lot of the time we can't do that. And so one technique I've showed you in this part of this lesson is a substitution that we can make effectively that allows us to write part of that differential equation, usually a sum of two terms in that differential equation, in a contracted form where we can make use of the product rule. Once we've contracted two sum terms together, we can then directly integrate, which is very, very useful indeed. When we're integrating those equations, very often you're going to have to use integration by parts. So one of the other aims of this part of this lesson was to reintroduce you to integration by parts and remind you how to do it. So I hope that helped.